So we did a problem exactly like this last class in the notes with graphing. All this has is a limit in front of it. It says limit as x approaches -2 of this function. So what that's asking you for is, where is the graph headed as you get closer and closer to -2? Well, we're going to go ahead and factor this. And the numerator is going to split x plus 2, x minus 1. And the denominator is going to split x plus 2, x plus 5. And so what is going on in this graph at -2? Good. Yes, there is a hole in the graph. So at -2, we have a hole. So let's find where that is. It's going to be -2 something. And we're going to take -2 and plug it back into what's left here. So the numerator would be -3. The denominator would be +3. And so that would give us -1. So we have a hole at -2, -1 on the graph. I just want to show you, I made this table here. I just want to show you what this looks like on the calculator. So I went ahead and typed this one into y equals. And we're going to go to table set right here. And we're going to start it at -2, which is the value that we're trying to look at. And then to fill in this table, I'm going to start with the outer edges, and we're going to kind of like zoom in on -2. So since those both have a 0.5, I want my table to count by halves. So I'm going to say that's 0.5. And then I'm going to go right here to table and get my values. So as you can see right there at -2, it says error, and that's because we said there's a hole there, so you don't get an actual value. But at -2.5, I have -1.4, and at -1.5, I have -0.714. So this is also a good opportunity for us to talk about decimals. For the AP exam, you need at least 3 decimal points. You can do more than that, but you need at least 3. And you don't have to round up or down. You can do what's called truncating, which means that you just take the first 3. I call it the first 3 that you see. So you need to do at least 3 decimal points. And then I'm going to go ahead and put the error in here as well. So again, we want to kind of zoom in on this point. So I'm going to bring it in a little further. And this time I want to count by 0.1 so that I can get these 2 values. So I'm going to go back to table set. I'm going to center it around -2 again, and this time I'm going to count by 0.1. So when I go to the table and get those values, -2.1, I see -1.069. And then for -1.9, I've got -0.935. And again, I'm just going to truncate that. I'm just going to take the first 3. You could put 0.936 if you want to round up. I just don't bother with that. I just always take the first 3. All right, and again, we're trying to zoom in on this point, so I'm just going to bring it in a little bit further, and now I'm going to count by 0.01. So going back to my table set, center it at -2. I'm going to count by 0.01. Go to my table and get my values. So I've got -1.007, and then I've got -0.993. And what I'm trying to get at here is, as we zoom in on -2, I realize that there is a hole, but these values on either side are getting closer and closer to -1. I didn't draw that very well. Let me write that again. And we already found that's where the hole was. But if we zoom in closer and closer, both sides are getting closer to -1. And so we say that that's what the limit is. The limit as x approaches -2 for this function equals -1. So the point is, a limit is just the graph's behavior. It doesn't matter whether there's actually a value there or not. In this case, it's a hole. It's just what are you getting closer and closer to as you zoom in. It's just the behavior of the graph. Where is it headed? And this graph is headed towards -1. So it doesn't matter that it's actually there or not. The other way I explain this, or like the analogy I like to use, is have you ever been like walking up the stairs and you're not paying attention and you get to the top of the staircase, but you take another step anyway by accident and then you stumble? Everyone's done this, admit it, okay? That's like a limit. There wasn't another step there, but if there had been, your foot would have landed right on it. It's just the behavior, it's just where you're headed, okay? So in order for a limit to exist, the same value is approached from both sides. So that happened in this case. Both sides are getting closer and closer to -1. If one side is getting closer to -1 and the other side's getting closer to, I don't know, 45, then you're not going to have a limit. There's no overall behavior as you zoom in on that part of the function. Your function cannot increase or decrease without bound. And without bound means forever and ever and ever and ever and ever. Now there's an exception for this, except for one-sided limits. You can approach positive or negative infinity as long as it's only from one side. The reason it can't be from both sides is you can't get agreement towards infinity or negative infinity. There's no like zooming in on that point and having this agreement. But if it's only from one side, then you can say positive or negative infinity. And then lastly, f of x cannot oscillate. And I'm going to show you an example of what that means. Let me type another function in the calculator here. We're going to look at sine of 1 over x. Oh, and this is another good time for us to have a conversation. When you're doing anything in the calculator that involves trig, you need to make sure that you are in Radian mode, which is what it should be on default anyway. But you do not want to take a quiz or test or the AP exam in degree mode because everything will come out wrong. Just make sure you're in Radian mode. And so we're going to look at this graph around 0. And I know you kind of can't see that real well. I'm going to zoom in on it. It looks kind of like a little heartbeat machine going back and forth there. Let me zoom in on it. Again, we're trying to figure out what the behavior is around 0. So let me zoom in again. And what this graph is doing is called oscillating. What's happening near 0 is it's going positive, negative, positive, negative, positive, negative. Like it can't make up its mind. It's just spastic here. And so there's no overall behavior around 0. And so you would say the limit does not exist. I'll zoom in one more time. If you zoom in far enough, it eventually just looks like a barcode. Yeah. And I think it'll just give up. Yeah, it didn't even graph anything around 0. It just gives up because there's no overall behavior. Someone asked to switch from radian to degrees. If you go to mode, which is right next to the second button, and look down the left-hand side, radian should be highlighted. And if you haven't messed with it, it will be what's highlighted. It's like the default option. No problem. All right, so that's what oscillating means. That doesn't come up real often, but it is just an interesting characteristic of a graph. Okay. So we are going to use this graph to answer all of these limit questions. And basically what you want to do is zoom in on that part of the graph and just see what the behavior is and see if there's agreement from the left and right. So this one says limit as x goes to -1 of this function. Here is -1. And if we zoom in on that, both sides of the graph are getting closer and closer to 0. So our answer is 0. The next one says limit as x goes to 1 of the function. Here is 1. Now I realize the point is up there, but we don't really care about that. We don't really care that there's a hole here either. If we were to take a microscope and zoom in on 1, both sides of the graph are getting closer and closer and closer to -1. So that's the behavior, and that's where the graph is headed. So we say the limit goes to -1. All right, this one says limit as x goes to -6, and then there's a little plus sign. Try and adjust this a bit, make that better. I think that's about as clear as I can get it. It says limit as x goes to -6, and there's a little plus sign. That means from the right. So we only want -6 from the right. So here's -6. This is the right-hand side. And since that graph is going down, we're going to say -infinity. So again, it's okay to get a positive or negative infinity as long as it's only from one side. And then this will kind of illustrate that as well. This says x going to -6 from the left. So here's -6. This is the left side. It's going down. So again, we're going to say -infinity. But this one just says limit as x goes to -6. It doesn't say from the left or from the right. That means overall. And so we would have to say does not exist for that. I realize both sides go down, but they can't ever like connect to each other. So we would have to say does not exist. All right, this one says -2, and there is a little negative sign. So it's -2 from the left. So here is -2. I don't need to worry about this side because we only want from the left. So as we approach from the left, the y value that we're getting closer and closer to is -1. Again, I don't care that there's a hole there. The y value is approaching -1. All right, this one says -2 from the right. So here's -2. And if we approach from the right, Abby, just go ahead and turn off your video. Okay, there we go. All right, if we approach from the right, the y value that's getting approached is like a little bit more than 2. Let's just go ahead and say 2.1. And then this one says limit as x approaches -2, and it doesn't say from the left or from the right, so they have to agree. Well, from the left, it's going to -1, and from the right, it's going to 2.1, so we would have to say does not exist. All right, this one says limit as x goes to -infinity. This is just end behavior, and you guys have been doing that since Algebra 2. We're just going to look at the left side of the graph. So as we go to -infinity, this graph is leveling off at 0. It won't ever actually touch 0. It's just going to get closer and closer and closer. Now this one says limit as x goes to +infinity, and that one is leveling off at -2. Again, it won't ever actually get there. It's just where it's headed. All right, this one says x approaching 4 from the left. So here is 4. This is the left-hand side. So I'm going to start to ask you, I've gone through a bunch of these. What is that answer going to be as we approach 4 from the left? Is no one feeling brave? I want to give, oh, there we go. Thank you. Yes, -infinity. Graph is going down, so -infinity. All right, this one says x approaching 4, and there's a little plus sign, so that means from the right. So here's 4. We're approaching from the right, and that one is going up, so that will be +infinity. And then this one just says x approaching 4 overall. There is no from the left or from the right. So since one side's going down and one side's going up, we have to say does not exist. Actually, anytime there's an asymptote and you're not told from the left or from the right, it's going to have to be does not exist. All right, so this one says -5 from the left. So here is -5, kind of right there on the function. As we approach from the left, the y value we're getting closer and closer to is -2. Or, you know, close enough. We'll say it is. And then this one's limit as x approaches 5. So here's 5. I realize there's a hole, but that doesn't matter. If we zoom in, like we're zooming in with a microscope, what y value is getting approached from both sides? As we get closer and closer to 5, what y value? Good, 0. Awesome. Now, these next ones are not limits. It is just the functional value. So for these, it's not behavior. This is not calculus. This is just algebra. This is there actually a point there? So let's find f of -2. Here's -2. We want the actual filled in point for -2, which is right there, like a little bit above 2. So we'll say 2.1. All right, f of -6. Well, there's an asymptote there, which means we don't have a point. So that would be does not exist. F of 1, there's a hole right here, but the actual point is up here at 4. So the actual functional value for that one is at 4. F of 5, we have a hole, so does not exist. F of 4, there's an asymptote, so does not exist. F of 0 is right here, so that would be -1. And then f of -1 is right here, so that would be, oh no, sorry, I pointed at the wrong thing. F of -1 would be right here, and so that would be 0. So that is the difference between a limit and an actual functional value. The limit is just the behavior. The functional value is there actually a point there? All right, do you guys want me to keep on going, or do you want another little break? Or are there any questions? Speak to me or type something. I don't think we need a break. Okay. I'm going to keep on going. If we finish early, we finish early, so that'll be good. I am going to do another break here at some point, though. All right, so that is limits. Now we're going to talk about continuity. There are 3 rules for a function to be continuous at a value c. So first of all, f of c exists. And what that means is there has to be a point there. If you don't have a point, you don't have continuity. So in layman's terms, there is a point. You have to have a point on the graph. That should make sense. If there's nothing there, then you're not continuous. The limit as x approaches c of the function has to exist. That means that there has to be behavior, meaning both sides of the graph have to approach the same thing. So yes, c can be any number. This is just like the in general. We're going to get to do some problems down here that have like actual numbers in them. But the limit existing means there's behavior. Both sides go to the same place. So there is a limit. So you have to have a point, you have to have a limit, and then they have to equal each other. So I'm going to take these 2 things and set them equal to each other. The limit as x approaches c for the function has to equal that functional value. So they equal each other. So there has to be a point, there has to be a limit, which means behavior, and then they have to agree with each other. So let's go through the types of discontinuities. Like, how can these rules get broken? So breaking the first rule, if you don't have a point, then your functional value does not exist. And there's a couple ways that can happen. If you don't have a point, instead you could have a hole, or you could have an asymptote. So those are the 2 ways that you could break the first rule. You could have a hole or you could have an asymptote, but there's not a point on the graph. The hole is called a removable discontinuity, and the asymptote is called non-removable. Removable is something that you could fix if you could just put the point right back in. Like if I could just fill this in, then we would be continuous. Non-removable is a more deep-seated problem. I can't fix this and make it continuous just by shoving a point back in there. So that is the difference between removable and non-removable. So on to the second rule. How could we break that rule? Well, that would be the limit as x approaches c of the function does not exist. And that means that both sides don't come to the same place. So you would have something like this. And so that would also be non-removable. I can't fix that just by filling this point back in. In fact, filling that point back in would make it worse because then it would fail the vertical line test. I would have 2 points at the same x value. So you can't fix that just by putting the point back. And this is also called a jump discontinuity because the graph jumps there. And then the way that the third rule gets broken, you have a point and you have a limit, but they just don't equal each other. So that is when the limit as x approaches c of the function does not equal the functional value. And that is this case where you have a hole and then the point is somewhere else. It's like, haha, I tricked you. The point is over here now. You have a point and you have a limit. Both sides come to the same value, but they don't equal each other. And that is also removable because if you could just put that point back, you could fix it. And then you would be continuous. So heads up, and I apologize ahead of time, this next section is going to be a little annoying because I'm going to have to keep flipping back to that other graph, but we will live. It will be okay. We're going to state whether the function is continuous, yes or no, and if it's a no, we have to give a reason why. And you have to use this limit notation. So our reason why is going to be one of those 3 things. Just instead of C, we'll have an actual number. But those are your 3 reasons why you're discontinuous. So let's look at x being 4. Here is 4. We are not continuous there. And the problem is that we don't have a point. There's an asymptote, so there's not actually a functional value there. So we will say no. And it is because this first rule got broken. There's not a point. So it would be f of 4 does not exist. So for -2, here is -2. We have a point for -2. So the first rule is okay. We've got a point. What we don't have is a limit. The 2 sides are not approaching the same thing. If we were to zoom in on -2, they're not both going to the same place. Kind of like up here, how both sides were going to -1. We don't have that. So this is going to be no. And it is this second rule here. The limit as x approaches -2 of the function does not exist. And if you want to be real fancy about that, or if on the AP exam, if they say check the limits from the left and from the right, you would say the limit as x approaches -2 from the left of the function doesn't equal the limit as we approach -2 from the right of the function. You're saying the left and the right don't come to the same place. I would accept this, but sometimes on the AP exam, they're like really picky and they want you to look at the left and the right. So I'm just showing you both options there. All right, what's the hardest thing about limits is all this notation and getting used to it. So let's look at 3. Here is 3. And the function is continuous at 3. We have a point, we have a limit, they agree. I can trace that part of the graph without lifting my pencil. So that one is just yes, which is nice because then we don't have to give any kind of explanation. All right, -6. I'm going to start asking you guys, what do you think? Is this a yes or a no? Are we continuous here, yes or no? Good. No. What is the problem? What do we not have at -6? What is lacking there? We do not have a point. Good. There is no point there. So we are going to say no. F of -6 does not exist. All right, so let's look at 5. Here is 5. I will go ahead and tell you we are not continuous there. And it is the same exact problem. We don't have a point. There's nothing filled in there. So I'm going to say no. F of 5 does not exist. There's no point there, so we can't be continuous. All right, let's look at 1. Here is 1. We have a point. It's up here. We have a limit. Both sides are approaching the same thing. but they don't equal each other. The limit is down here at -1, and the point is up there at 4. So this is that third rule. You're going to say, no, the limit as x approaches 1 of this function doesn't equal f of 1. The limit was going to -1, and the point was up there at 4. So those two do not equal each other. Now, the rest of these are over an interval. So if there's any issue anywhere within the interval, then we're going to have a problem. This one is from 8 to infinity. So let's see, here's 8. From 8 onwards, I can trace that without lifting my pencil off the paper. I don't have any holes or problems. It's going to go on forever and ever. So we would be continuous from 8 onwards. So that is just a yes. This, I realize it looks like a coordinate point. I'm sorry about that. It's the interval from -5 to -2, and the parentheses just mean we're not including those points. So we don't have to worry about -5 and -2, just everything in between them. So here is -5, here is -2. I'm ignoring everything else on the graph except for things between -5 and -2. We would be continuous there. Everything is good within that interval. I realize there's a hole here, but it is okay because we're not including the -2. So we didn't need for there to be a hole there. That was fine. Now from 5 to 7, we have brackets. So that means we need 5 and 7 to be part of that interval. So we will need to look at 5 and 7. So let's look at that interval. Here is 5, here is 7. Everything in between is kind of okay, but we do have an issue on this one. We are missing a point at 5, and we need to include 5 because there were brackets on it. So this one's going to be a no. We do not have a point at 5. So f of 5 does not exist. And then last one of these, we want between -1 and 1, and they're brackets, so we are including it. So here is -1 to 1, and we are including it, so we do have a problem. It's the same issue as when we looked at 1. That limit and that point don't agree. So it's actually going to be this exact same reason, just with one little change. I'm basically just going to copy that over. I just have to change one little thing. If our interval is only from -1 to 1, it's like nothing else on this graph exists. We are only looking at this one little piece. So I have to approach 1 from the left. I can't approach 1 from the right because we're not looking at that. This is our interval and this is it. So this is going to be no. And again, I'm pretty much copying over this answer. I just need to include its limit as x approaches 1 from the left. Again, because we are not looking at anything to the right of 1. Of that function does not equal f of 1. The limit was down there at -1. The actual point was up there at 4. So they did not agree with each other. All right, and I am going to give you another little break here. Let's just finish this last one, though, on this page. This says, find p so that this function would be continuous at -1. Well, if we want these two pieces of the piecewise function to meet up, then we're going to set them equal to each other. So that's your first step, set them equal. If you want there to be continuity, the two pieces have to meet up. And then specifically, we want them to meet up at x being -1. So we're going to plug in -1 for x. So everywhere there is an x, I'm going to put -1. And then we're just going to solve for p. This would be 1 minus 2, which would be -1. And then add over the 1. So you get 0 equals -p. So if you divide by the negative, you're still just going to get 0. So if you want to make a piecewise function be continuous, just set the two pieces equal. That will make sure that they meet up, and then at specifically the point that you are talking about there.